Okay, class. So in section 9.6, we are talking about functions and surfaces. So right now, in the past, you've had y as a function of x. Y equals a function of x. But what if you had a function of two variables? Okay, what if you had a function of two variables instead of one? Okay, so in other words, they give an example here, for instance, like temperature. So it says that the temperature, let me bring that down a little bit here. So the temperature at a point on the surface of the Earth at any given time depends on longitude and latitude. So the temperature, okay, and I'm looking right here. Let me just actually, I actually like this, but I want to highlight it. Man, okay. Let me take this off here. Okay, so a temperature on the surface of the Earth at any given time depends on the longitude and latitude of the point. So we can think of a temperature function as being a function of two variables, x and y. Okay, in other words, to talk about temperature, temperature is not a function of just one variable, it's a function of two variables. So T is a function of x and y. So that's called a function. That's called a function of two variables. That's what that's called. And you know, for functions of two variables, okay, we can talk about, for instance, domains and ranges. So like in example 2 here, they say for each of the following functions, okay, let me make sure. For each of the following functions, evaluate the function when x is 3 and y is 2, and find and sketch the domain. So the first function here is defined as the square root of x plus y plus 1 divided by x minus 1. That's the first function. Okay. And so if we're gonna evaluate the function at the point 3, 2, all you do is you let x equals 3 and y equals 2 and substitute in, and you get your value of the function. So at 3, 2, the function equals square root of 6 over 2. Now, of course, we might be interested, well, we are interested in the domain of this function. So this particular function here, and I'm kind of highlighting it and moving as we go, we know that in the denominator, there's a problem at x equals 1, right? Because x cannot equal, we can't have 0 in the denominator, so x can't equal 1. But in the numerator, you have a square root function, and you can't have the square root of a negative number. So that means that x plus y plus 1 would have to be greater than or equal to 0. So we have two conditions that have to be satisfied for this domain. And we can write the domain as the set of all coordinates, x, y coordinates, such that x plus y plus 1 is greater than or equal to 0, and x is not equal to 1. Okay, we can write the domain that way. So if we write the domain that way, then graphically, this is what the domain looks like. Okay, so the domain is a two-dimensional domain. And you notice in the picture there in figure 1, well, the domain doesn't consist of the vertical asymptote x equals 1 because you can't allow x to equal 1. That would make the denominator of this function equal to 0. But also, x plus y plus 1 equals 0, well, that's the same as y equals x minus 1. If you look at the boundary line of where the shaded region is there, that's the line y equals x minus 1. No, that's the line y equals negative x plus 1 in this figure 1, because that boundary line has a slope of negative 1 and a y-intercept of negative 1. So, and then the shading would be for all the points above that boundary line, except where the intercept is, where that asymptote is, x equals 1. So that's what your domain looks like. And so you see, when we have functions of two variables, the domain is in the xy plane. So just like when we have functions of one variable, we can talk about a domain. When we have functions of two variables, we can also talk about a domain. Now, for this second problem, the function of x and y is x times the log of y squared minus x. Well, clearly, you can't have the log of a negative number. So y squared minus x would have to be greater, and you can't have the log of 0 either. So y squared would have to be greater than x, right? Or x would have to be, hold on. If y squared is greater than x, then x would be less than y squared. And so what would the domain look like for that function? What would the domain look like for that function? It would look like what you see in this picture here. Okay, those are all, so the boundary line is x equals y squared, and x would be less than y squared. That's the domain of the function. So that's going to be all that shading to the left. So you see, this is how we deal with functions of two variables. This is how we work with them. Now, let's say you wanted to graph a linear function. Okay, let's say you wanted to graph a linear function, and we're not going to finish all of this section tonight. We'll have to continue it on Thursday, but let's continue here. So, if you have a function of two variables, then you can set z equal to f of xy, and so you can graph the function, the values of the function, using z coordinates, and that's what you see here in figure 3. You see there? You're plotting it. You have a function of x and y that traces out a surface in three-dimensional space. And in figure 3, every point on the surface has coordinates x, y, and then z, which is the function of x and y. Do you see how that works in figure 3? Are there any questions so far?
Professor?
Yes, Alexander.
Sorry, this is kind of off topic. I was just wondering, for the classwork assignments, it's like not showing the.
Oh, we'll get to that. I know what you're asking about, section 9.6, right?
Oh yeah, but also the
I,
web assigned homework. Some of them
that's
like
right.
9.5, 9.4.
I will get to that. I promise, Alexander. Don't worry.
Okay, sorry, Professor.
I'm going to look at this example 4, and then I'm going to address that right after we're done here. We're almost done. Very good question. Very good question. So example 4 says graph the function f of xy equals 6 minus 3x minus 2y. Well, you see, f of xy, we can think of that as z. So z equals 6 minus 3x minus 2y. That's the equation of a plane. That's the equation of a plane. You see, so here, what they're saying is this here. I'd like to try to highlight it if I can. Let me just try to. Just give me a moment here. I'm going to get it. I'll put it in pink. So this function is the function for the equation of a plane. And it's easy to get the intercepts of the plane. For instance, if you let y and z equal 0, you get x equals 2. And that forms the x-intercept of the plane. Okay, so it's easy to get a feel for what the plane looks like. And that's an example. You've just graphed your first function of two variables. So what we're going to actually focus on in the next class, on Thursday's class, is just looking at how we would graph functions of two variables, for instance, using MATLAB. This is where we're going to end tonight on section 9.6, and we will continue that section on Thursday. So are there any questions before and then I'll talk about the homework, but are there any questions before I stop the recording? Okay, excellent.